Hey there, it's Andrew Turner from Central High School, about to start talking about exponential functions for our KCS at Home summer edition. So let's jump into a little bit about exponential functions. So exponential functions, you got to start there. The whole conversation begins with the exponent laws, because everything about exponential is referring to exponents. Just to review exponents are that little tiny number in the top right corner above a number. A lot of times it's just the number 1, and it looks invisible a lot of time. But 2 to the third power really means 2 times 2 times 2. 2 times 2 is 4, times 2 again would be 8. So not 6, it's not 6. 2 times 2 times 2 is 8. And so whenever things are exponential, they're multiplying rapidly and they grow exponentially in a curve. Or maybe they decay, going down in a curve exponentially. So just to review a little bit of the exponent rules, anytime you are multiplying variables, you really add the powers together. Or anytime you are putting an exponent on another exponent, that's when you should multiply. Or if you find yourselves dividing variables, x divided by x, that's when you should subtract their powers. And if exponents really mean how many times you multiply when they're negative, it really means how many times you're going to divide by that value. And so there's, an invisible 1 in front of everything, so that's this 1 in the numerator. And so whenever you have a negative power, it really means that variable is going to move into the denominator and represent as a positive exponent how many times you're going to divide by that value. And then very common mistakes, anytime you have an exponent of 0, it's not 0 as the outcome, but the value of 1. So for example, 60 to the 0 power is 1. But 7y to the 0, well, that would be 7. Well, why is that? Well, this is really 7 times 1. Y to the 0 would be 1. And then 7 times 1 is 7. So be careful to make sure that 0 as a power only affects what it is on its base. Okay. So for example, I'm going to do a few of your practice problems and kind of help you understand a little bit how I've mastered those power rules. So I'm going to talk a little bit about that. In school, you first learn to add, maybe in 1st or 2nd grade, and then you learn how to subtract, and by 3rd or 4th grade, you're working on multiplication, and then you work on division, and then eventually you start talking about exponents. And so when we are talking about putting together exponents, it's easy to use this progression as a way of understanding how to put things together, but you have to understand that you're kind of 2 levels up. Exponents already represent multiplication, so you're kind of already starting a little higher in the progression. So let me show you what I mean by that. For example, we're doing 4x to the 3rd times 2x to the 3rd. So, 4 times 2, that's 8. I shouldn't think about these rules as affecting integers or coefficients in that way. But when we're talking about x to the 3rd times x to the 3rd, we really want to go 2 steps down from what's happening. Instead of multiplying, we really want to add those powers together to get x to the 6th. And the reason mathematically why you want to go down 2 levels is because, again, exponents already represent multiplication. So if you're multiplying, we really want to add those powers together. And so for the next step, we may want to think about, division. So in number 2, I see an x to the 5th and then an x to the 1. And so division, let's go 2 steps down. And if we want to put those together, 5 minus 1, that would be x to the 4th. Same thing for the 6 and the 2. 6 minus 2, that would be y. Oh, sorry, I messed up. I want that in the numerator because I really noticed that y to the 6, y to the 2, there's more in the numerator than the denominator, so I want to make sure that I just put all of my answers kind of over 1, but dividing by 1 is really not necessary. So let's look at one like, let's talk about number 3. So you're putting a power on a power. So we may want to think about 2 raised to the negative 2. We'll talk about that here in a minute. But when we put powers on powers, you need to go 2 steps down. And that would mean we really need to multiply those together. So 3 and times -2, that'd be -6. And then -2 times -3, that'd be +6. Let me move myself out of the way here. And so now I want to kind of clean some stuff up because I really don't want anything to be left as a negative. So I really want to say, well, 2 to the -2, that really means I'm dividing by 2 twice. And so I really want to move that to the bottom. Same thing with my x. It's negative, so I want it to move to the bottom and become positive. And then I want to leave y to the 6 in the numerator because it was not a negative power, it was positive. Well, 2 squared, I could simplify 2 squared to be 4, and then that could kind of be my final answer there. Let's do maybe 2 more. Here I noticed that all of this is to the 0 power, so this becomes a 1. But then that negative is still waiting outside of it, so this one kind of results as -1 for this answer. And I mentioned that negative powers kind of move into the denominator, but if they're already in the denominator, it's kind of like it's got another fraction in a fraction, which we definitely don't want to do that. And so we talk about complex fractions. We may want to think about if it's negative in the denominator, then it could move up to the numerator to become positive. Okay, if it's negative in the denominator, you could move it up and make it a positive power, and it's now in the numerator. So let's talk a little bit about explicit formulas for geometric sequences. We talked a little bit about arithmetic in a former video. We're going to talk a little bit more about geometric. And so geometric, you got to lock in on what that first number is in the sequence. What is that common ratio? What are you multiplying by to get to the next term? And then n-1 is just kind of a part of your power. So I've taken these tables, so we're going to do some work with that, and we're going to kind of put some of that in a chart down here. And so I'm going to rewrite that explicit formula, and then let's kind of talk about what we're kind of looking for here. So explicit formula, my first number in that first table, table A, is -2. And if you were to use the common ratio of +3, that's what you're multiplying by every time. -2 times 3, -6. -6 times 3 is -18. And anytime you're looking for this common ratio value, you should divide the second number by the first number to understand what that common ratio value is. n-1, simply part of the power. Okay? And so the next thing I want to do is I want to just kind of, maybe I'll just keep that consistent. Let's just do that with all of them. The next one I start with 1,234. And if I was to divide that second number with that first number, or if we just really look at what's going on with the decimals here, it's almost like you're dividing by 10. Really, it's like you're multiplying by 1/10. And then your power is still n-1. 45, 90, 180. It looks like you're starting at 45. 90 divided by 45, it looks like you're doubling. 90 times 2 is 180. So there's your n-1 as your power. And then, with this last one, you start with -5. That's your first number. But if you were to divide -2.5 by -5, you're going to see that basically you are multiplying by half over and over and over to get the next term in the sequence. Okay? I'm going to check my time. Plenty of time. So when we talk about that constant ratio, when we talk about that y-intercept, that can really be identified fairly quickly from one of these models. So for example, that constant ratio, that's your R value, that's your 3, or your 1/10. Or for this next one, you were multiplying by 2. Or for this last one, you were multiplying by half. Kind of felt like you were dividing by 2, but really it's multiplying by 2. And so if we were to kind of think about these sequences as an exponential function where they don't have that n-1 affecting it, we would kind of have to think, okay, well, what number was in front of that in the sequence? What value would have been one term to the left? So if I was to not multiply by 3, But to divide by 3, we could kind of go back in a sense and figure out that this could have been negative 2/3, still multiplying by 3, but now it's just to the x power. So that power not being affected by 1, if I want to really live at the origin, I need to kind of go back a step to kind of understand, well, what number would have been in front of that. For example, for this one, I would have had the number 340. I would have been multiplying by 1/10, but then I wouldn't have needed that -1. Again, that's because I've kind of stepped in front of that term. I've kind of gone back to that y-intercept term, not your first term. So for this one, 45 divided by 2, kind of going back there, that'd be 22. Let's just say 45 over 2. We just leave it as a fraction. You're multiplying by 2, but now we don't have that -1 in the power because we've kind of moved where that first value was starting. One last one, what number would have been in front of -5? Would have been -10. Still would have divided by 2 to get that -5, but we wouldn't have needed that -1 power. So that's important because when we're looking for the y-intercept, we really need to go find where is this sequence at the 0th term. These are the first terms of the sequence, and the y-intercept really lives where the input is 0. So we kind of had to back up a little bit to understand where those values would have been. And really, when I say back up, I mean you are undoing your process. If over here you're multiplying by 2, we'll divide by 2 to move backward. You could have also used these formulas and plugged in 0, and it would have calculated that other value for you. All right, so that's kind of some advanced stuff for sure. Let's talk about just a general graph of an exponential function. So I want to start by looking at my function and recognizing that this is using that second style, where this value right here isn't the first number. This is your y-intercept, this -3 value. This represents what's going to happen when you plug in 0. For example, if I was to plug in 0, we talked about with the power rules, 1/4 to the 0 power would have been 1. And then if you multiply that by -3, you're getting out -3. So just like what we were talking about on the sequence videos, sorry, not the sequence videos, what we were talking about the other slide, we kind of had to notice that the power wasn't -1 to note that -3 was a y-intercept value, not the first term. Okay, so if I was to plug in a 1 for this, 1/4 to the 1 would be 1/4. And if I multiply that by -3, you get -3/4. And if I plug in a 2 here, that's going to make 1/16. That -3 is going to multiply against that 1, making -3/16. So I'm just going to kind of make a quick sketch of this. 1, -3/4. 2 gives me -3/16, and so forth and so forth. So now if I was to plug in -1, -1 is going to end up going as an exponent on both of these. But from the video earlier, we talked about how negatives are going to basically change or reciprocate this. That -1 makes 4 go to the top as a +1 power. It makes 1 go to the bottom. And so just putting -1 on 1/4 really turns that into a 4. Multiply that by -3, you're getting -12. So -1 gives you -12. And what we're going to see is that is curving down infinitely in the down direction, and then it is moving up and to the right a little bit at a time. Plugging in -2, basically this would have come out to be, let's see, 4 squared over 1 squared, that would have been 16, times -3 would be -48. So that's going to be way down at the very bottom. Okay. In the next video, we're going to talk a little bit more about some word problems with exponential, and we will also talk a little bit more about growth and decay. So I'll see you in just a moment.